Oscilloscope.
An oscilloscope, previously called an oscillograph, and informally known as a scope, CRO, or DSO, is a type of electronic test instrument that allows observation of constantly varying signal voltages, usually as a two-dimensional plot of one or more signals as a function of time. Non-electrical signals can be converted to voltages and displayed. Oscilloscopes are used to observe the change of an electrical signal over time, such that voltage and time describe a shape which is continuously graphed against a calibrated scale. The observed waveform can be analyzed for such properties as amplitude, frequency, rise time, time interval, distortion and others. Modern digital instruments may calculate and display these properties directly. Originally, calculation of these values required manually measuring the waveform against the scales built into the screen of the instrument. The oscilloscope can be adjusted so that repetitive signals can be observed as a continuous shape on the screen. A storage oscilloscope allows single events to be captured by the instrument and displayed for a relatively long time, allowing human observation of events too fast to be directly perceptible. Oscilloscopes are used in the sciences, medicine, engineering, and telecommunications industry. General-purpose instruments are used for maintenance of electronic equipment and laboratory work. Special-purpose oscilloscopes may be used for such purposes as analyzing an automotive ignition system or to display the waveform of a heartbeat as an electrocardiogram. Before the advent of digital electronics, oscilloscopes used cathode ray tubes, CRTs, as their display element, hence were commonly referred to as CROs, and linear amplifiers for signal processing. Storage oscilloscopes used special storage CRTs to maintain a steady display of a single brief signal. CROs were later largely superseded by digital storage oscilloscopes, DSOs, with thin panel displays, fast analog to digital converters and digital signal processors. DSOs without integrated displays, sometimes known as digitizers, are available at lower cost and use a general-purpose digital computer to process and display waveforms.
Features and uses. Description.
The basic oscilloscope, as shown in the illustration, is typically divided into four sections: the display, vertical controls, horizontal controls and trigger controls. The display is usually a CRT or LCD panel which is laid out with both horizontal and vertical reference lines referred to as the graticule. In addition to the screen, most display sections are equipped with three basic controls: a focus knob, an intensity knob and a beam finder button. The vertical section controls the amplitude of the displayed signal. This section carries a volts per division, volts div, selector knob, an AC/DC ground selector switch and the vertical, primary, input for the instrument. Additionally, this section is typically equipped with a vertical beam position knob. The horizontal section controls the time base or sweep of the instrument. The primary control is the seconds per division, sec div, selector switch. Also included is a horizontal input for plotting dual X-Y axis signals. The horizontal beam position knob is generally located in this section. The trigger section controls the start event of the sweep. The trigger can be set to automatically restart after each sweep or it can be configured to respond to an internal or external event. The principal controls of this section will be the source and coupling selector switches. An external trigger input, EXT input, and level adjustment will also be included. In addition to the basic instrument, most oscilloscopes are supplied with a probe as shown. The probe will connect to any input on the instrument and typically has a resistor of 10 times the oscilloscope's input impedance. This results in a 1-10x attenuation factor, but helps to isolate the capacitive load presented by the probe cable from the signal being measured. Some probes have a switch allowing the operator to bypass the resistor when appropriate.
Size and portability.
Most modern oscilloscopes are lightweight, portable instruments that are compact enough to be easily carried by a single person. In addition to the portable units, the market offers a number of miniature battery-powered instruments for field service applications. Laboratory-grade oscilloscopes, especially older units which use vacuum tubes, are generally benchtop devices or may be mounted into dedicated carts. Special-purpose oscilloscopes may be rack-mounted or permanently mounted into a custom instrument housing.
Inputs.
The signal to be measured is fed to one of the input connectors, which is usually a coaxial connector such as a BNC or UHF type. Binding posts or banana plugs may be used for lower frequencies. If the signal source has its own coaxial connector, then a simple coaxial cable is used. Otherwise, a specialized cable called a scope probe, supplied with the oscilloscope, is used. In general, for routine use, an open wire test lead for connecting to the point being observed is not satisfactory, and a probe is generally necessary. General-purpose oscilloscopes usually present an input impedance of 1 MΩ in parallel with a small but known capacitance such as 20 pF. This allows the use of standard oscilloscope probes. Scopes for use with very high frequencies may have 50 ohm inputs, which must be either connected directly to a 50 ohm signal source or used with ZO or active probes. Less frequently used inputs include 1, or 2, for triggering the sweep, horizontal deflection for XY mode displays, and trace brightening darkening, sometimes called Z-axis inputs.
Probes.
Open wire test leads, flying leads, are likely to pick up interference, so they are not suitable for low-level signals. Furthermore, the leads have a high inductance, so they are not suitable for high frequencies. Using a shielded cable, that is, coaxial cable, is better for low-level signals. Coaxial cable also has lower inductance, but it has higher capacitance. A typical 50 ohm cable has about 90 pF per meter. Consequently, a 1 meter direct, 1x, coaxial probe will load a circuit with a capacitance of about 110 pF and a resistance of 1 MΩ. To minimize loading, attenuator probes, for example, 10x probes, are used. A typical probe uses a 9 MΩ series resistor shunted by a low-value capacitor to make an RC-compensated divider with the cable capacitance and scope input. The RC time constants are adjusted to match. For example, the 9 MΩ series resistor is shunted by a 12.2 pF capacitor for a time constant of 110 microseconds. The cable capacitance of 90 pF in parallel with the scope input of 20 pF and 1 MΩ, total capacitance 110 pF, also gives a time constant of 110 microseconds. In practice, there will be an adjustment so the operator can precisely match the low-frequency time constant, called compensating the probe. Matching the time constants makes the attenuation independent of frequency. At low frequencies, where the resistance of R is much less than the reactance of C, the circuit looks like a resistive divider. At high frequencies, resistance much greater than reactance, the circuit looks like a capacitive divider. The result is a frequency-compensated probe for modest frequencies that presents a load of about 10 megohms shunted by 12 pF. Although such a probe is an improvement, it does not work when the timescale shrinks to several cable transit times. Transit time is typically 5 nanoseconds. In that time frame, the cable looks like its characteristic impedance, and there will be reflections from the transmission line mismatch at the scope input and the probe that causes ringing. The modern scope probe uses lossy low-capacitance transmission lines and sophisticated frequency shaping networks to make the 10x probe perform well at several hundred MHz. Consequently, there are other adjustments for completing the compensation. Probes with 10-1 attenuation are by far the most common. For large signals, and slightly less capacitive loading, 101 probes are not rare. There are also probes that contain switches to select 10-1 or direct 1-1 ratios, but one must be aware that the 1-1 setting has significant capacitance, tens of pF, at the probe tip, because the whole cable's capacitance is now directly connected. Most oscilloscopes allow for probe attenuation factors, displaying the effective sensitivity at the probe tip. Historically, Some auto-sensing circuitry used indicator lamps behind translucent windows in the panel to illuminate different parts of the sensitivity scale. To do so, the probe connectors, modified BNCs, had an extra contact to define the probe's attenuation. A certain value of resistor, connected to ground, encodes the attenuation. Because probes wear out, and because the auto-sensing circuitry is not compatible between different makes of oscilloscope, auto-sensing probe scaling is not foolproof. Likewise, manually setting the probe attenuation is prone to user error, and it is a common mistake to have the probe scaling set incorrectly. Resultant voltage readings can then be wrong by a factor of 10. There are special high-voltage probes which also form compensated attenuators with the oscilloscope input. The probe body is physically large, and some require partly filling a canister surrounding the series resistor with volatile liquid fluorocarbon to displace air. At the oscilloscope end is a box with several waveform trimming adjustments. For safety, a barrier disc keeps one's fingers distant from the point being examined. Maximum voltage is in the low tens of kilovolt. Observing a high-voltage ramp can create a staircase waveform with steps at different points every repetition, until the probe tip is in contact. Until then, a tiny arc charges the probe tip, and its capacitance holds the voltage, open circuit. As the voltage continues to climb, another tiny arc charges the tip further. There are also current probes, with cores that surround the conductor carrying current to be examined. One type has a hole for the conductor, and requires that the wire be passed through the hole. They are for semi-permanent or permanent mounting. However, other types, for testing, have a two-part core that permit them to be placed around a wire. Inside the probe, a coil wound around the core provides a current into an appropriate load, and the voltage across that load is proportional to current. However, this type of probe can sense AC only. A more sophisticated probe includes a magnetic flux sensor, Hall effect sensor, in the magnetic circuit. The probe connects to an amplifier, which feeds low-frequency current into the coil to cancel the sensed field. The magnitude of that current provides the low-frequency part of the current waveform, right down to DC. The coil still picks up high frequencies. There is a combining network akin to a loudspeaker crossover network.
Front panel controls. Focus control.
This control adjusts CRT focus to obtain the sharpest, most detailed trace. In practice, focus needs to be adjusted slightly when observing quite different signals, which means that it needs to be an external control. Flat panel displays do not need focus adjustments and therefore do not include this control.
Intensity control.
This adjusts trace brightness. Slow traces on CRT oscilloscopes need less, and fast ones, especially if not often repeated, require more. On flat panels, however, trace brightness is essentially independent of sweep speed, because the internal signal processing effectively synthesizes the display from the digitized data.
Astigmatism.
Can also be called shape, or spot shape. Adjusts the relative voltages on two of the CRT anodes such that a displayed spot changes from elliptical in one plane through a circular spot to an ellipse at 90 degrees to the first. This control may be absent from simpler oscilloscope designs or may even be an internal control. It is not necessary with flat panel displays.
Beam finder.
Modern oscilloscopes have direct coupled deflection amplifiers, which means the trace could be deflected off-screen. They also might have their beam blanked without the operator knowing it. To help in restoring a visible display, the beam finder circuit overrides any blanking and limits the beam deflected to the visible portion of the screen. Beam finder circuits often distort the trace while activated.
Graticule.
The graticule is a grid of squares that serve as reference marks for measuring the displayed trace. These markings, whether located directly on the screen or on a removable plastic filter, usually consist of a 1 cm grid with closer tick marks, often at 2 mm, on the center vertical and horizontal axis. One expects to see 10 major divisions across the screen. The number of vertical major divisions varies. Comparing the grid markings with the waveform permits one to measure both voltage, vertical axis, and time, horizontal axis. Frequency can also be determined by measuring the waveform period and calculating its reciprocal. On old and lower-cost CRT oscilloscopes, the graticule is a sheet of plastic, often with light diffusing markings and concealed lamps at the edge of the graticle. The lamps had a brightness control. Higher-cost instruments have the graticule marked on the inside face of the CRT, to eliminate parallax errors. Better ones also had adjustable edge illumination with diffusing markings. Diffusing markings appear bright. Digital oscilloscopes, however, generate the graticule markings on the display in the same way as the trace. External graticules also protect the glass face of the CRT from accidental impact. Some court oscilloscopes with internal graticules have an unmarked tinted sheet plastic light filter to enhance trace contrast. This also serves to protect the faceplate of the CRT. Accuracy and resolution of measurements using a graticule is relatively limited. Better instruments sometimes have movable bright markers on the trace that permit internal circuits to make more refined measurements. Both calibrated vertical sensitivity and calibrated horizontal time are set in 1-2-5-10 steps. This leads, however, to some awkward interpretations of minor divisions. At 2, each of the 5 minor divisions is 0.4, so one has to think 0.4, 0.8, 1.2, and 1.6, which is rather awkward. One Tektronix plugin used a 1-2.5-5-10 sequence, which simplified estimating. The 2.5 did not look as neat, but was very welcome.
Timebus controls.
These select the horizontal speed of the CRT spot as it creates the trace. This process is commonly referred to as the sweep. In all but the least costly modern oscilloscopes, the sweep speed is selectable and calibrated in units of time per major graticule division. Quite a wide range of sweep speeds is generally provided, from seconds to as fast as picoseconds, in the fastest, per division. Usually, a continuously variable control, often a knob in front of the calibrated selector knob, offers uncalibrated speeds, typically slower than calibrated. This control provides a range somewhat greater than that of consecutive calibrated steps, making any speed available between the extremes.
Hold-off control.
Found on some better analog oscilloscopes, this varies the time, hold-off, during which the sweep circuit ignores triggers. It provides a stable display of some repetitive events in which some triggers would create confusing displays. It is usually set to minimum, because a longer time decreases the number of sweeps per second, resulting in a dimmer trace. See hold-off for a more detailed description.
Vertical sensitivity, coupling, and polarity controls.
To accommodate a wide range of input amplitudes, a switch selects calibrated sensitivity of the vertical deflection. Another control, often in front of the calibrated selector knob, offers a continuously variable sensitivity over a limited range from calibrated to less sensitive settings. Often the observed signal is offset by a steady component, and only the changes are of interest. A switch, AC position, connects a capacitor in series with the input that passes only the changes, provided that they are not too slow. Slow would mean visible. However, when the signal has a fixed offset of interest, or changes quite slowly, the input is connected directly, DC switch position. Most oscilloscopes offer the DC input option. For convenience, to see where 0 volts input currently shows on the screen, many oscilloscopes have a third switch position, GND, that disconnects the input and grounds it. Often, in this case, the user centers the trace with the vertical position control. Better oscilloscopes have a polarity selector. Normally, a positive input moves the trace upward, but this permits inverting, positive deflects the trace downward.
Horizontal sensitivity control.
This control is found only on more elaborate oscilloscopes. It offers adjustable sensitivity for external horizontal inputs.
Vertical position control.
The vertical position control moves the whole displayed trace up and down. It is used to set the no-input trace exactly on the center line of the graticle, but also permits offsetting vertically by a limited amount. With direct coupling, adjustment of this control can compensate for a limited DC component of an input.
Horizontal position control.
The horizontal position control moves the display sidewise. It usually sets the left end of the trace at the left edge of the graticle, but it can displace the whole trace when desired. This control also moves the XY mode traces sidewise in some instruments, and can compensate for a limited DC component as for vertical position.
Dual trace controls.
Please see dual and multiple trace oscilloscopes, below. Each input channel usually has its own set of sensitivity, coupling, and position controls, although some 4-trace oscilloscopes have only minimal controls for their third and fourth channels. Dual-trace oscilloscopes have a mode switch to select either channel alone, both channels, or, in some, an XY display, which uses the second channel for X deflection. When both channels are displayed, the type of channel switching can be selected on some oscilloscopes. On others, the type depends upon time-bus setting. If manually selectable, channel switching can be free-running, asynchronous, or between consecutive sweeps. Some Philips dual-trace analog oscilloscopes had a fast analog multiplier, and provided a display of the product of the input channels. Multiple trace oscilloscopes have a switch for each channel to enable or disable display of that trace's signal.
Delayed sweep controls.
Please see delayed sweep, below. These include controls for the delayed sweep time-bus, which is calibrated, and often also variable. The slowest speed is several steps faster than the slowest main sweep speed, although the fastest is generally the same. A calibrated multi-turn delay time control offers wide-range, high-resolution delay settings. It spans the full duration of the main sweep, and its reading corresponds to graticule divisions, but with much finer precision. Its accuracy is also superior to that of the display. A switch selects display modes, main sweep only, with a brightened region showing when the delayed sweep is advancing, delayed sweep only, or, on some, a combination mode. Good court oscilloscopes include a delayed sweep intensity control, to allow for the dimmer trace of a much faster delayed sweep that nevertheless occurs only once per main sweep. Such oscilloscopes also are likely to have a trace separation control for multiplex display of both the main and delayed sweeps together.
Sweep trigger controls.
Please see triggered sweep, below. A switch selects the trigger source. It can be an external input, one of the vertical channels of a dual or multiple trace oscilloscope, or the AC line, mains, frequency. Another switch enables or disables auto-trigger mode, or selects single sweep, if provided in the oscilloscope. Either a spring return switch position or a push-button arm single sweeps. A level control varies the voltage on the waveform which generates a trigger, and the slope switch selects positive going or negative going polarity at the selected trigger level.
Basic types of sweep. Triggered sweep.
To display events with unchanging or slowly, visibly, changing waveforms, but occurring at times that may not be evenly spaced, modern oscilloscopes have triggered sweeps. Compared to simpler oscilloscopes with sweep oscillators that are always running, triggered sweep oscilloscopes are markedly more versatile. A triggered sweep starts at a selected point on the signal, providing a stable display. In this way, triggering allows the display of periodic signals such as sine waves and square waves, as well as non-periodic signals such as single pulses, or pulses that do not recur at a fixed rate. With triggered sweeps, the scope will blank the beam and start to reset the sweep circuit each time the beam reaches the extreme right side of the screen. For a period of time, called hold-off, extendable by a front panel control. On some better oscilloscopes, the sweep circuit resets completely and ignores triggers. Once hold-off expires, the next trigger starts a sweep. The trigger event is usually the input waveform reaching some user-specified threshold voltage, trigger level, in the specified direction, going positive or going negative, trigger polarity. In some cases, variable hold-off time can be really useful to make the sweep ignore interfering triggers that occur before the events one wants to observe. In the case of repetitive, but quite complex waveforms, variable hold-off can create a stable display that cannot otherwise practically be obtained.
Hold-off.
Trigger hold-off defines a certain period following a trigger during which the scope will not trigger again. This makes it easier to establish a stable view of a waveform with multiple edges which would otherwise cause another trigger.
Example.
Imagine the following repeating waveform. The green line is the waveform, the red vertical partial line represents the location of the trigger, and the yellow line represents the trigger level. If the scope was simply set to trigger on every rising edge, this waveform would cause 3 triggers for each cycle. Assuming the signal is fairly high frequency, the scope would probably look something like this. Except that on the scope, each trigger would be the same channel, and so would be the same color. It is desired to set the scope to only trigger on one edge per cycle, so it is necessary to set the hold-off to be slightly less than the period of the waveform. That will prevent it from triggering more than once per cycle, but still allow it to trigger on the first edge of the next cycle.
Automatic sweep mode.
Triggered sweeps can display a blank screen if there are no triggers. To avoid this, these sweeps include a timing circuit that generates free-running triggers so a trace is always visible. Once triggers arrive, the timer stops providing pseudo-triggers. Automatic sweep mode can be deselected when observing low repetition rates.
Recurrent sweeps.
If the input signal is periodic, the sweep repetition rate can be adjusted to display a few cycles of the waveform. Early, tube, oscilloscopes and lowest-cost oscilloscopes have sweep oscillators that run continuously, and are uncalibrated. Such oscilloscopes are very simple, comparatively inexpensive, and were useful in radio servicing and some TV servicing. Measuring voltage or time is possible, but only with extra equipment, and is quite inconvenient. They are primarily qualitative instruments. They have a few, widely spaced, frequency ranges, and relatively wide-range continuous frequency control within a given range. In use, the sweep frequency is set to slightly lower than some submultiple of the input frequency, to display typically at least 2 cycles of the input signal, so all details are visible. A very simple control feeds an adjustable amount of the vertical signal, or possibly, a related external signal, to the sweep oscillator. The signal triggers beam blanking and a sweep retrace sooner than it would occur free-running, and the display becomes stable.
Single sweeps.
Some oscilloscopes offer these. The sweep circuit is manually armed, typically by a push button or equivalent. Armed means it's ready to respond to a trigger. Once the sweep is complete, it resets, and will not sweep until rearmed. This mode, combined with an oscilloscope camera, captures single-shot events. Types of trigger include external trigger, a pulse from an external source connected to a dedicated input on the scope. Edge trigger, an edge detector that generates a pulse when the input signal crosses a specified threshold voltage in a specified direction. These are the most common types of triggers. The level control sets the threshold voltage, and the slope control selects the direction, negative or positive going. The first sentence of the description also applies to the inputs to some digital logic circuits. Those inputs have fixed threshold and polarity response. Video trigger, a circuit that extracts synchronizing pulses from video formats such as PAL and NTSC and triggers the time bus on every line, a specified line, every field, or every frame. This circuit is typically found in a waveform monitor device, although some better oscilloscopes include this function. Delayed trigger, which waits a specified time after an edge trigger before starting the sweep. As described under delayed sweeps, a trigger delay circuit, typically the main sweep, extends this delay to a known and adjustable interval. In this way, the operator can examine a particular pulse in a long train of pulses. Some recent designs of oscilloscopes include more sophisticated triggering schemes. These are described toward the end of this article.
Delayed sweeps.
More sophisticated analog oscilloscopes contain a second time bus for a delayed sweep. A delayed sweep provides a very detailed look at some small selected portion of the main time bus. The main time bus serves as a controllable delay, after which the delayed time bus starts. This can start when the delay expires, or can be triggered, only, after the delay expires. Ordinarily, the delayed time bus is set for a faster sweep, sometimes much faster, such as 1001. At extreme ratios, jitter in the delays on consecutive main sweeps degrades the display, but delayed sweep triggers can overcome that. The display shows the vertical signal in one of several modes, the main time bus, or the delayed time bus only, or a combination thereof. When the delayed sweep is active, the main sweep trace brightens while the delayed sweep is advancing. In one combination mode, provided only on some oscilloscopes, the trace changes from the main sweep to the delayed sweep once the delayed sweep starts, although less of the delayed fast sweep is visible for longer delays. Another combination mode multiplexes, alternates, the main and delayed sweeps so that both appear at once. A trace separation control displaces them. DSOs allow waveforms to be displayed in this way, without offering a delayed time bus as such.
Dual and multiple trace oscilloscopes.
Oscilloscopes with two vertical inputs, referred to as dual trace oscilloscopes, are extremely useful and commonplace. Using a single beam CRT, they multiplex the inputs, usually switching between them fast enough to display two traces apparently at once. Less common are oscilloscopes with more traces. Four inputs are common among these, but a few, Kikizui, for one, offered a display of the sweep trigger signal if desired. Some multi-trace oscilloscopes use the external trigger input as an optional vertical input, and some have third and fourth channels with only minimal controls. In all cases, the inputs, when independently displayed, are time multiplexed, but dual trace oscilloscopes often can add their inputs to display a real-time analog sum. Inverting one channel provides a difference, provided that neither channel is overloaded. This difference mode can provide a moderate performance differential input. Switching channels can be asynchronous, that is, free-running, with trace blanking while switching, or after each horizontal sweep is complete. Asynchronous switching is usually designated chopped, while sweep synchronized is designated alt. A given channel is alternately connected and disconnected, leading to the term chopped. Multi-trace oscilloscopes also switch channels either in chopped or alternate modes. In general, chop mode is better for slower sweeps. It is possible for the internal chopping rate to be a multiple of the sweep repetition rate, creating blanks in the traces, but in practice this is rarely a problem. The gaps in one trace are overwritten by traces of the following sweep. A few oscilloscopes had a modulated chopping rate to avoid this occasional problem. Alternate mode, however, is better for faster sweeps. True dual-beam CRT oscilloscopes did exist, but were not common. One type, COSA, UK had a beam splitter plate in its CRT, and single-ended deflection following the splitter. Others had two complete electron guns, requiring tight control of axial, rotational, mechanical alignment in manufacturing the CRT. Beam splitter types had horizontal deflection common to both vertical channels, but dual-gun oscilloscopes could have separate time bases, or use one time base for both channels. Multiple-gun CRTs, up to 10 guns, were made in past decades. With 10 guns, the envelope, bulb, was cylindrical throughout its length. Also see CRT invention in oscilloscope history.
The vertical amplifier.
In an analog oscilloscope, the vertical amplifier requires the signal to be displayed. In better oscilloscopes, it delays them by a fraction of a microsecond, and provides a signal large enough to deflect the CRT's beam. That deflection is at least somewhat beyond the edges of the graticle, and more typically some distance off-screen. The amplifier has to have low distortion to display its input accurately, it must be linear, and it has to recover quickly from overloads. As well, its time domain response has to represent transients accurately, minimal overshoot, rounding, and tilt of a flat pulse top. A vertical input goes to a frequency-compensated step attenuator to reduce large signals to prevent overload. The attenuator feeds a low-level stage, or a few, which in turn feed gain stages, and a delay line driver if there is a delay. Following are more gain stages, up to the final output stage which develops a large signal swing, tens of volts, sometimes over 100 volts, for CRT electrostatic deflection. In dual and multiple trace oscilloscopes, an internal electronic switch selects the relatively low-level output of one channel's amplifiers and sends it to the following stages of the vertical amplifier, which is only a single channel, so to speak, from that point on. In free-running, chopped mode, the oscillator, which may be simply a different operating mode of the switch driver, blanks the beam before switching, and unblanks it only after the switching transients have settled. Partway through the amplifier is a feed to the sweep trigger circuits, for internal triggering from the signal. This feed would be from an individual channel's amplifier in a dual or multi-trace oscilloscope, the channel depending upon the setting of the trigger source selector. This feed precedes the delay, if there is one, which allows the sweep circuit to unblank the CRT and start the forward sweep, so the CRT can show the triggering event. High-quality analog delays add a modest cost to an oscilloscope, and are omitted in oscilloscopes that are cost-sensitive. The delay, itself, comes from a special cable with a pair of conductors wound around a flexible, magnetically soft core. The coiling provides distributed inductance, while a conductive layer close to the wires provides distributed capacitance. The combination is a wideband transmission line with considerable delay per unit length. Both ends of the delay cable require matched impedances to avoid reflections.
XY mode.
Most modern oscilloscopes have several inputs for voltages, and thus can be used to plot one varying voltage versus another. This is especially useful for graphing IV curves, current versus voltage characteristics, for components such as diodes, as well as Lissajous patterns. Lissajous figures are an example of how an oscilloscope can be used to track phase differences between multiple input signals. This is very frequently used in broadcast engineering to plot the left and right stereophonic channels, to ensure that the stereo generator is calibrated properly. Historically, stable Lissajous figures were used to show that two sine waves had a relatively simple frequency relationship, a numerically small ratio. They also indicated phase difference between two sine waves of the same frequency. The XY mode also allows the oscilloscope to be used as a vector monitor to display images or user interfaces. Many early games, such as Tennis for Two, used an oscilloscope as an output device. Complete loss of signal in an XY-CRT display means that the beam strikes a small spot, which risks burning the phosphor. Older phosphors burned more easily. Some dedicated XY displays reduce beam current greatly, or blank the display entirely, if there are no inputs present.
Bandwidth.
As with all practical instruments, oscilloscopes do not respond equally to all possible input frequencies. The range of frequencies an oscilloscope can usefully display is referred to as its bandwidth. Bandwidth applies primarily to the y-axis, although the x-axis sweeps have to be fast enough to show the highest frequency waveforms. The bandwidth is defined as the frequency at which the sensitivity is 0.707 of that at DC or the lowest AC frequency, a drop of 3 decibels. The oscilloscope's response will drop off rapidly as the input frequency is raised above that point. Within the stated bandwidth, the response will not necessarily be exactly uniform, or flat, but should always fall within a +0 to -3 decibels range. One source states that there is a noticeable effect on the accuracy of voltage measurements at only 20% of the stated bandwidth. Some oscilloscope specifications do include a narrower tolerance range within the stated bandwidth. Probes also have bandwidth limits and must be chosen and used to properly handle the frequencies of interest. To achieve the flattest response, most probes must be compensated, an adjustment performed using a test signal from the oscilloscope, to allow for the reactance of the probe's cable. Another related specification is rise time. This is the duration of the fastest pulse that can be resolved by the scope. It is related to the bandwidth approximately by bandwidth in Hertz x rise time in seconds equals 0.35. For example, an oscilloscope intended to resolve pulses with a rise time of 1 nanosecond would have a bandwidth of 350 MHz. In analog instruments, the bandwidth of the oscilloscope is limited by the vertical amplifiers in the CRT or other display subsystem. In digital instruments, the sampling rate of the analog-to-digital converter, ADC, is a factor, but the stated analog bandwidth, and therefore the overall bandwidth of the instrument, is usually less than the ADC's Nyquist frequency. This is due to limitations in the analog signal amplifier, deliberate design of the anti-aliasing filter that precedes the ADC, or both. For a digital oscilloscope, a rule of thumb is that the continuous sampling rate should be 10 times the highest frequency desired to resolve. For example, a 20 megasample-second rate would be applicable for measuring signals up to about 2 MHz. This allows the anti-aliasing filter to be designed with a 3 dB down point of 2 MHz and an effective cutoff at 10 MHz, the Nyquist frequency, avoiding the artifacts of a very steep, brick wall filter. A sampling oscilloscope can display signals of considerably higher frequency than the sampling rate if the signals are exactly, or nearly, repetitive. It does this by taking one sample from each successive repetition of the input waveform, each sample being at an increased time interval from the trigger event. The waveform is then displayed from these collected samples. This mechanism is referred to as equivalent time sampling. Some oscilloscopes can operate in either this mode or in the more traditional real-time mode at the operator's choice.
Other features.
Some oscilloscopes have cursors, which are lines that can be moved about the screen to measure the time interval between 2 points, or the difference between 2 voltages. A few older oscilloscopes simply brighten the trace at movable locations. These cursors are more accurate than visual estimates referring to graticule lines. Better quality general-purpose oscilloscopes include a calibration signal for setting up the compensation of test probes. This is, often, a 1 kHz square wave signal of a definite peak-to-peak voltage available at a test terminal on the front panel. Some better oscilloscopes also have a squared-off loop for checking and adjusting current probes. Sometimes the event that the user wants to see may only happen occasionally. To catch these events, some oscilloscopes, known as storage scopes, preserve the most recent sweep on the screen. This was originally achieved by using a special CRT, a storage tube, which would retain the image of even a very brief event for a long time. Some digital oscilloscopes can sweep at speeds as slow as once per hour, emulating a strip chart recorder. That is, the signal scrolls across the screen from right to left. Most oscilloscopes with this facility switch from a sweep to a strip chart mode at about 1 sweep per 10 seconds. This is because otherwise, the scope looks broken, it's collecting data, but the dot cannot be seen. In current oscilloscopes, digital signal sampling is more often used for all but the simplest models. Samples feed fast analog to digital converters, following which all signal processing, and storage, is digital. Many oscilloscopes have different plug-in modules for different purposes, for example, high-sensitivity amplifiers of relatively narrow bandwidth, differential amplifiers, amplifiers with 4 or more channels, sampling plug-ins for repetitive signals of very high frequency, and special-purpose plug-ins, including audio ultrasonic spectrum analyzers, and stable offset voltage direct couple channels with relatively high gain.
Examples of use.
One of the most frequent uses of scopes is troubleshooting malfunctioning electronic equipment. One of the advantages of a scope is that it can graphically show signals, where a voltmeter may show a totally unexpected voltage. A scope may reveal that the circuit is oscillating. In other cases, the precise shape or timing of a pulse is important. In a piece of electronic equipment, for example, the connections between stages, for example electronic mixers, electronic oscillators, amplifiers, may be probed for the expected signal, using the scope as a simple signal tracer. If the expected signal is absent or incorrect, some preceding stage of the electronics is not operating correctly. Since most failures occur because of a single faulty component, each measurement can prove that half of the stages of a complex piece of equipment either work, or probably did not cause the fault. Once the faulty stage is found, further probing can usually tell a skilled technician exactly which component has failed. Once the component is replaced, the unit can be restored to service, or at least the next fault can be isolated. This sort of troubleshooting is typical of radio and TV receivers, as well as audio amplifiers, but can apply to quite different devices such as electronic motor drives. Another use is to check newly designed circuitry. Very often a newly designed circuit will misbehave because of design errors, bad voltage levels, electrical noise etc. Digital electronics usually operate from a clock, so a dual trace scope which shows both the clock signal and a test signal dependent upon the clock is useful. Storage scopes are helpful for capturing rare electronic events that cause defective operation. Pictures of use.
Automotive use.
First appearing in the 1970s for ignition system analysis, automotive oscilloscopes are becoming an important workshop tool for testing sensors and output signals on electronic engine management systems, braking and stability systems.
Selection.
For work at high frequencies and with fast digital signals, the bandwidth of the vertical amplifiers and sampling rate must be high enough. For general-purpose use, a bandwidth of at least 100 MHz is usually satisfactory. A much lower bandwidth is sufficient for audio frequency applications only. A useful sweep range is from 1 second to 100 nanoseconds, with appropriate triggering and, for analog instruments, sweep delay. A well-designed, stable, trigger circuit is required for a steady display. The chief benefit of a quality oscilloscope is the quality of the trigger circuit. Key selection criteria of a DSO, apart from input bandwidth, is the sample memory depth and sample rate. Early DSOs in the mid to late 90s only had a few KB of sample memory per channel. This is adequate for basic waveform display, but does not allow detailed examination of the waveform or inspection of long data packets, for example. Even entry-level, less than $500, modern DSOs now have 1 MB or more of sample memory per channel, and this has become the expected minimum in any modern DSO. Often this sample memory is shared between channels, and can sometimes only be fully available at lower sample rates. At the highest sample rates, the memory may be limited to a few tens of KB. Any modern real-time sample rate DSO will have typically 5 to 10 times the input bandwidth and sample rate. So a 100 MHz bandwidth DSO would have 500 milliseconds per second -1 GSS sample rate. The theoretical minimum sample rate required using SYN-XX interpolation is 2.5 times the bandwidth. Analog oscilloscopes have been almost totally displaced by digital storage scopes except for use exclusively at lower frequencies. Greatly increased sample rates have largely eliminated the display of incorrect signals, known as aliasing, that was sometimes present in the first generation of digital scopes. The problem can still occur when, for example, viewing a short section of a repetitive waveform that repeats at intervals thousands of times longer than the section viewed, for example a short synchronization pulse at the beginning of a particular television line, with an oscilloscope that cannot store the extremely large number of samples between one instance of the short section and the next. The use test equipment market, particularly online auction venues, typically have a wide selection of older analog scopes available. However, it is becoming more difficult to obtain replacement parts for these instruments, and repair services are generally unavailable from the original manufacturer. Used instruments are usually out of calibration, and recalibration by companies with the equipment and expertise usually charges more than the second-hand value of the instrument. As of 2007, a 350 MHz bandwidth, BW, 2.5 gigasamples per second, GSS, dual-channel digital storage scope costs about $7,000 new. On the lowest end, an inexpensive hobby-grade single-channel DSO can now be purchased for under $90 as of June 2011. These often have limited bandwidth and other facilities, but fulfill the basic functions of an oscilloscope.
Software.
Many oscilloscopes today provide one or more external interfaces to allow remote instrument control by external software. These interfaces, or buses, include GPIB, Ethernet, serial port, and USB.
Types and models.
The following section is a brief summary of various types and models available. For a detailed discussion, refer to the other article.
Cathode ray oscilloscope (CRO).
The earliest and simplest type of oscilloscope consisted of a cathode ray tube, a vertical amplifier, a timepiece, a horizontal amplifier and a power supply. These are now called analog scopes to distinguish them from the digital scopes that became common in the 1990s and 2000s. Analog scopes do not necessarily include a calibrated reference grid for size measurement of waves, and they may not display waves in the traditional sense of a line segment sweeping from left to right. Instead, they could be used for signal analysis by feeding a reference signal into one axis and the signal to measure into the other axis. For an oscillating reference and measurement signal, this results in a complex looping pattern referred to as a Lissajous curve. The shape of the curve can be interpreted to identify properties of the measurement signal in relation to the reference signal, and is useful across a wide range of oscillation frequencies.
Dual beam oscilloscope.
The dual-beam analog oscilloscope can display two signals simultaneously. A special dual-beam CRT generates and deflects two separate beams. Although multi-trace analog oscilloscopes can simulate a dual-beam display with chop and alternate sweeps, those features do not provide simultaneous displays. Real-time digital oscilloscopes offer the same benefits of a dual-beam oscilloscope, but they do not require a dual-beam display. The disadvantages of the dual-trace oscilloscope are that it cannot switch quickly between the traces and it cannot capture too fast transient events. In order to avoid this problem, a dual-beam oscilloscope is used.
Analog storage oscilloscope.
Trace storage is an extra feature available on some analog scopes. They use direct view storage CRTs. Storage allows the trace pattern that normally decays in a fraction of a second to remain on the screen for several minutes or longer. An electrical circuit can then be deliberately activated to store and erase the trace on the screen.
Digital oscilloscopes.
While analog devices make use of continually varying voltages, digital devices employ binary numbers which correspond to samples of the voltage. In the case of digital oscilloscopes, an analog-to-digital converter, ADC, is used to change the measured voltages into digital information. The digital storage oscilloscope, or DSO for short, is now the preferred type for most industrial applications, although simple analog CROs are still used by hobbyists. It replaces the electrostatic storage method used in analog storage scopes with digital memory, which can store data as long as required without degradation and with uniform brightness. It also allows complex processing of the signal by high-speed digital signal processing circuits. A standard DSO is limited to capturing signals with a bandwidth of less than half the sampling rate of the ADC, called the Nyquist limit. There is a variation of the DSO called the digital sampling oscilloscope that can exceed this limit for certain types of signal, such as high-speed communications signals, where the waveform consists of repeating pulses. This type of DSO deliberately samples at a much lower frequency than the Nyquist limit and then uses signal processing to reconstruct a composite view of a typical pulse. A similar technique, with analog rather than digital samples, was used before the digital era in analog sampling oscilloscopes. A digital phosphor oscilloscope, DPO, uses color information to convey information about a signal. It may, for example, display infrequent signal data in blue to make it stand out. In a conventional analog scope, such a rare trace may not be visible.
Mixed-signal oscilloscopes.
A mixed-signal oscilloscope, or MSO, has two kinds of inputs, a small number of analog channels, typically 2 or 4, and a larger number of digital channels, typically 16. It provides the ability to accurately time correlate analog and digital channels, thus offering a distinct advantage over a separate oscilloscope and logic analyzer. Typically, digital channels may be grouped and displayed as a bus with each bus value displayed at the bottom of the display in hex or binary. On most MSOs, the trigger can be set across both analog and digital channels.
Handheld oscilloscopes.
Handheld oscilloscopes are useful for many test and field service applications. Today, a handheld oscilloscope is usually a digital sampling oscilloscope, using a liquid crystal display. Many handheld and bench oscilloscopes have the ground reference voltage common to all input channels. If more than one measurement channel is used at the same time, all the input signals must have the same voltage reference, and the shared default reference is the earth. If there is no differential preamplifier or external signal isolator, this traditional desktop oscilloscope is not suitable for floating measurements. Occasionally an oscilloscope user will break the ground pin in the power supply cord of a benchtop oscilloscope in an attempt to isolate the signal common from the earth ground. This practice is unreliable since the entire stray capacitance of the instrument cabinet will be connected into the circuit. Since it is also a hazard to break a safety ground connection, instruction manuals strongly advise against this practice. Some models of oscilloscope have isolated inputs, where the signal reference level terminals are not connected together. Each input channel can be used to make a floating measurement with an independent signal reference level. Measurements can be made without tying one side of the oscilloscope input to the circuit signal common or ground reference. The isolation available is categorized as shown below.
PC-based oscilloscopes.
A new type of oscilloscope is emerging that consists of a specialized signal acquisition board, which can be an external USB or parallel port device, or an internal add-on PCI or ISA card. The user interface and signal processing software runs on the user's computer, rather than on an embedded computer as in the case of a conventional DSO.
Related instruments.
A large number of instruments used in a variety of technical fields are really oscilloscopes with inputs, calibration, controls, display calibration, etc., specialized and optimized for a particular application. Examples of such oscilloscope-based instruments include waveform monitors for analyzing video levels in television productions and medical devices such as vital function monitors and electrocardiogram and electroencephalogram instruments. In automobile repair, an ignition analyzer is used to show the spark waveforms for each cylinder. All of these are essentially oscilloscopes, performing the basic task of showing the changes in one or more input signals over time in an XY display. Other instruments convert the results of their measurements to a repetitive electrical signal, and incorporate an oscilloscope as a display element. Such complex measurement systems include spectrum analyzers, transistor analyzers, and time domain reflectometers, TDRs. Unlike an oscilloscope, these instruments automatically generate stimulus or sweep a measurement parameter.
History.
The Braun tube was known in 1897, and in 1899 Jonathan Zanuck equipped it with beam-forming plates and a magnetic field for sweeping the trace. Early cathode ray tubes had been applied experimentally to laboratory measurements as early as the 1920s, but suffered from poor stability of the vacuum and the cathode emitters. V. K. Zworykin described a permanently sealed, high-vacuum cathode ray tube with a thermionic emitter in 1931. This stable and reproducible component allowed General Radio to manufacture an oscilloscope that was usable outside a laboratory setting. After World War II, surplus electronic parts became the basis of revival of Heathkit Corporation, and a $50 oscilloscope kit made from such parts was a first market success.